Good morning, everybody. Let's talk about polynomial functions. This is still going to be looking at graphs, but it's going to be much easier because you're not really having to talk about the whole graph or all the parts of the graph. There's really only one thing in particular we need to look at. This is going to make things look so confusing. It's so much easier than this. Basically, A with the little n is just saying the leading coefficient of the first variable, plus the leading coefficient of the second variable, right? The first one minus 1, and then that exponent minus 1. In other words, we're counting down. Okay, if this starts at 10, it's going to go 10, 9, 8, blah, 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 2, 1, 0. Okay. I'm not sure. I mean, it looks fancy math. I guess that's why they write it like that. But a polynomial function, you've seen them all the time. Okay, a polynomial could be a trinomial, could be something like a binomial, could just be a regular old x, a monomial where we just have one. Even just a solid number like 5 is still a monomial. Anything that only has numbers and exponents is pretty much variables with exponents is pretty much a polynomial. Okay, no fractions, no square roots, no funky stuff, no parentheses. It's just a string of numbers, and importantly, a string of numbers where you count down. No negative exponents. Everything's a real number. N is a positive number. There's no negative exponents and crazy stuff like that. A to the power, or a little n, we already know this actually, is the leading coefficient, okay? Because a with the little n is the number out front right here, and so that's the leading coefficient. We saw this with our rational functions. A with the little n is the leading coefficient. Now, because we've already done rational functions, this is a piece of cake here. Tell me the degree, tell me the leading coefficient. Starting with maybe some of the easier ones, degree 2, degree 3, degree 4, degree 5, right? Your degree is your highest exponent. We've already kind of talked about this with our rational functions, but you're literally just looking for the highest exponent you got and going with it. Your leading coefficient is the number in front of that, right? That's your a little n, so that would be 12. If you only see a negative sign, what would it be? Do you guys know? Negative 1. That's super easy. We got negative 3 coming up next. We've got positive 9. Now let's talk about our degrees and leading coefficients for these two. They're shorter, but they're almost harder because they are shorter. If you haven't noticed the pattern already, 2, 3, 4, 5, this one is going to be a degree 1. If you have only an x, then you have 1x, then you have a degree 1. So that's going to be a degree 1. So the leading coefficient is just going to be the number in front of it, which is going to be negative 5. Now, it can definitely be tricky for this. This is, how many x's do you have? You have x to the power of 0, technically. And so this is considered to be a degree 0 polynomial. And the number in front of that is a 4. So definitely a little bit weird with that constant function where y is always 4. But at the end of the day, it's not too hard. And now again, we already know all this stuff. Now we're going to breeze through these notes, but up next is we're going to talk about polynomial parent functions. Okay, so we've seen all different types of parent functions: linear, quadratic, cubic. We've seen square roots, cube roots. We've seen absolute values. We've seen square roots. I already said we've seen exponents, logs, rational functions. A polynomial parent function would have to be one that has no square roots, no absolute values. It's just y, x, and an exponent, okay? And so what we've got here is, basically y equals, and this one's a little weird for us. It's kind of like x to the power of 0. And that's almost making it too complicated on purpose. You know, you could write it like this, or any other number, 1, 2, 3, 4, 5, but this is really probably the parent function for a constant function, even though that makes it pretty complicated, right? Linear is just y equals x to the power of 1. Quadratic is y equals x squared. Cubic is y equals x cubed. I think I'm lagging here. There we go. And we can go ahead and flip over the bag, right? Quartic is going to be y equals x to the 4th. Quintic is going to be y equals x to the 5th. Yeah, it just counts up. Basically 0, 1, 2, 3, 4, 5. And so looking at these, we're going to talk about how does the function look? What does the parent function look like? And we already know how 4 of these 6 look. Okay, we've already got these on our parent functions worksheet, right? Our constant function. Let me get this set up. Our constant function is just a y equals 1. It would just look like that. Our linear function is just y equals x. And so that would look like this. Our quadratic function is y equals x squared. That's our parabola. That's our U shape. Anything that looks kind of like a U, if you want to kind of do it on 2 different sides, that's fine. Always looks good on one side and bad on the other. And cubic. We've also seen a cubic before. Okay, cubic has that same kind of U shape over here, but on this negative side, it goes down. Now, what we're going to see is that with our quadratic, when you square a number, you turn it positive, right? And so if we take 100 and we square it, we're going to get a positive number. If we take negative 100 and we square it, we're also going to get a positive number. And that's why they're going up on both sides. When we have cubics, that is not the case. 100 cubed would make a positive. Negative 100 cubed would make a negative. And so that's why we're going up, but also down on the left. So that kind of pattern continues when you're doing quartic. Okay, we don't do a lot of x to the power of 4, but if you take, a number like maybe negative 2 to the power of 4, that would be negative 2 times negative 2 times negative 2 times negative 2. 4 negative 2's. These 2 would make a positive. These 2 would make a positive. And these 2 positives would make a positive. And so if you have 4 of something, it's going to be positive no matter what. Doesn't matter if it's negative 100 or negative 1 or negative 2. It's going to be positive. And so we have the same kind of thing happening here where our function is going to be positive at both the ends. But a little bit differently, your quartic might look like a U, but instead of drawing it like a U, it also might look like a W. Now, to be very clear, if we go to Desmos and we type in x to the power of 4, it's going to look like a u. And it looks a little bit like a strange u. You can kind of see how it's a little bit different than our x squared, right? Our x squared is the blue graph. Our x to the 4th is the red graph. It still looks like a u, though. But if we added in some other stuff, like maybe a 3x cubed, maybe we've got a negative 2x squared, maybe we've got a plus 6x, maybe just a regular old x, maybe we have a plus 1. You can see how we're going to get some really kind of wavy shapes. It kind of looks like a W here, where it's going to go down, up, and then have another little swerve there as it goes up. If we change this to a minus, you can also see how it's kind of taking a W style shape as it goes through there. Down, up, down, up. What's happening is every time that we are adding on a letter x here, we're kind of getting a turn added on to our graph. Okay? So if you picture this with me, if we've got our graph and we have, y equals x, it's kind of like an up. And then if we get x squared, okay, it looks like a u, but then we get x cubed. Okay, it looks like a square, but then we get x to the 4th. Okay, it looks like a w, but then we get x to the 5th. It's going to go back up. And so every time we add on an exponent, it's going to give us one more kind of kink in the dragon's tail, if that makes any sense at all, right? Sometimes these can start to look like some crazy cool dragons when you're looking at them. Sea serpents, maybe. So our x to the 5th, it's the same kind of idea, right? We know we're going to be low and then high, because we know that with odd exponents, a negative number is going to stay negative and a positive number is going to stay positive. But what we'll get is we'll get an up and then a down and then an up and then a down and then an up. Now, again, technically, if we go to Desmos and we just type in a regular old x to the power of 5, it's going to look almost the same as the cubic, right? The red and the green. Almost the same. But if we add in some of this extra spicy stuff, minus x to the power of 4, if we have plus x to the power of 3, if we have plus x squared, if we have plus x, maybe we have minus 3, we can really start them with all of these different things here. Every little change that we make is going to change our graph quite a bit, right? So all of these different x values allow us to change our graph up, right? We basically have A, B, C, D, E, F, all these different numbers that we can make crazy different things with. Yeah, I don't know what I've just done there, but now it's going up, down forever. Then it's going up a long way. So these polynomial functions, oh, my bad. We can really mess with them a bunch and get some really crazy shapes out of them. But this is the most turns that a power 5 graph could have. 1, 2, 3, 4, 5 different kind of up and then down and then up and then down and then up. All right, all that being said, here's the real idea here, okay? We need to be able to do end behavior without looking at the actual graph. Just by looking at the function, can you tell the end behavior? And where this comes from is us looking at this chart of these 6 things and making a realization that on the even side, okay, so we'll call this the even side over here. On this side of the chart, terrible outline, by the way, we have the same end behavior, right? Out, out, up, 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 up. And if this happened to be a negative x squared, it would be down, down. So on this even side, we're handling this nice same in behavior. On this odd side, of course, it's the opposite, right? We've got up, down, up, down, up, down. And if this was negative x cubed, it would be up, down. So even degree, we're going to have the same in behavior. Odd degree, we're going to have opposite in behavior. So we're looking at this. We notice that we have a 4 here, so we know that it's even. And that means we're going to have the same in behavior. And then we need to know if it's going to be an upwards facing W or if it's going to be a downwards facing W, right? Because our two options are either infinity, infinity, or negative infinity, negative infinity. We do that by looking at this positive 4 out front, the leading coefficient, okay? If that number is positive, it's going to be up. If that number is negative, it's going to be down. And so we realize that this 4 tells us that it is a positive even graph. That tells us it is going to be something like this. And so we should have infinity, infinity as both of our in behaviors. And that's it. I mean, in reality, this takes like 3 seconds to answer one of these questions, okay? If I go over to number 2, I see that we have an even function. I see that we have a negative leading coefficient. That means that we should have same, but an upside down u. That means we should have negative infinity, negative infinity. Now with odd functions, it can be a bit more tricky. Okay, we have to remember that a positive odd function would look like a regular old line, and that a negative odd function would look like a downwards going line, right? And that this means infinity, negative infinity, or negative infinity, positive infinity. Well, okay, hold up. That's the x values. The y values would be infinity, negative infinity. That wasn't very good. So let's knock this out, okay? When we have these odd functions, I know this one's an odd function because we have that degree 3, and then I have a positive odd function. So positive odd function basically means your x values and your y values are going to be the same. As my x goes positive, I'm going to positive infinity. As my x goes negative, I'm going to negative infinity. So these are going to be the same as they were before. Same in behavior, same in behavior. If I have an odd positive. Over here, obviously, I'm sure you guys are onto the pattern here. I've got an odd negative now, so that's going to be an odd negative. That means I'm going to have opposites of this in behavior, right? On the positive side, I'm down. On the negative side, I'm up. All right, we got 4 people in class. We got 4 answers. I'm going to give you guys 20 seconds to knock out this 5 and 6. There's only 4 possibilities, right? Even positive, even negative, odd positive, odd negative. So once you figure out which of these 4 you are, you can literally just copy these in behaviors straight onto 5 and 6. Again, I'll give you guys 10, 15 more seconds. Shouldn't be too tough. All right, we're almost done with these notes. I know I may be rushing you, but you guys are such smart students. It's probably not hurting you too bad. Number 5, let's just go left to right. Sienna, you're up first. What do you think? Even, odd, positive, negative. What do you think, Sienna? Even, I agree. Positive or negative? Can't quite hear, but I'm going to go with it. You said negative. I trust that you did. So, Caitlin, you're up next. What do you think? If we have even negative, that tells you we should have the same end behavior. And so what's your two end behaviors you got here, Caitlin? And easy, right? They're both the same, piece of cake. Literally, I can just notice even negative, they have the same end behavior. So I could have just copied these two answers and gone with that. Damaris, you're up next, my man. Even or odd function, positive or negative? Yep, easy peasy. Devin, what do you got for the end behavior for this number 6 one? So what do you got for these two answers going here and here? It's either positive infinity or negative infinity. Positive infinity, and then what's the bottom one? So Devin's going with also positive infinity. I know that even functions will have the same, but I know that odd functions will never have the same in behavior. So you were right with this first one. That means the bottom one has got to be negative infinity. Okay, you've got an odd positive graph, so you've got a graph that looks like this, and so you've got a positive infinity, negative infinity function. And then with the odds, again, the trick is that with the odds, if you're odd positive, these answers are going to be the same, right? Negative infinity, negative infinity. Everything is the way it kind of should be. If you've got an odd negative, you're going to have to flip these two. All right, so let's make our little cheat sheet. This is a very valuable little study guide thing here. If we have, I know you guys are probably sick of study guides at this point. We're not really making one here, but we're just filling this in. Even degree positive leading coefficient, okay? That means up, up. Simple as that, right? That means our answer is going to be infinity and infinity. Now, what's crazy about, well, it's not crazy necessarily, but what's weird about this is that in the middle here, our graph literally might look like this. But we know for sure, after it does all the zigzag accordion looking stuff in the middle, guaranteed it's going up on both ends, okay? And so that's why I'm not really connecting these two arrows, because we really don't know what's going on in the middle, but we are guaranteed on the ends that it is going up and up. If we have an odd positive, we are going up and we are going down. So that would be infinity and negative infinity. And again, the same idea is true, right? In the middle, it might look like this, or it might just look like this. Right? We don't really know what's going on in the middle, but on the ends, we know they have to be opposite and that things should be kind of the same. And then let's just wrap this up, right? Even negative would be down, down, and odd negative would be from the high down to the low. Kind of backwards of what you would think. That's the whole idea, right? Even degrees are guaranteed to be the same in behavior. Odd degrees are guaranteed to be opposite in behavior. You know, if you want to use a highlighter and make some sort of chart like this, I guess you could. So we can now finish this worksheet. It's one of the first times we've done every question on a worksheet, actually. What we're trying to do now is look at the picture and tell me, is it even or odd? Is it positive or negative? So we're going to go through the same 4 of you guys again. You guys are killing it today. Number 7, going back to Sienna. Sienna, is this an even function or an odd function? I would agree. This is an even function, and we know it's an even function because it has the same in behavior. So it's got to be even. Caitlin, do you think it's an even positive or even negative? I agree. Even negative because we have down, down. And so that's an even negative. Mary, do you think number 8's an odd or an even function? Of course. And Devin, what do you think? Positive or negative? This one's a little tricky. You've kind of been stuck with the 2 tricky ones, man. I'm sorry about that. So because we're going from low to high, like kind of how you would want your money to go, then that's a good thing, then that's a positive, right? So, you know, if I told you that if you gave me some money right here, I could make it look like this, you'd probably take me up on that, right? Because it would go up, maybe down a little bit, but it would end up up. So that's a good thing. That's a positive thing. If I told you that I'd take your money and it would look like that, give it to me here, get it back here, you probably would disagree with me. So that would be a negative function. Okay, that is polynomials. That is thinking about even and odd functions, how their in behavior correlates between the two. That's it. We're done. I guess we didn't even go to Desmos. Obviously, we looked a little bit on here, but hope that helps.